how this algorithms comes to this prediction. So in order to do this, so in order to make this, and if you can see, go for a deep learning or any other algorithms, these algorithms are so complex that you can't derive how this result has come into. So in order to make these decisions, in order to have a trust on this, whatever the predictions that we have come up with the explainable or the explainable AI, that the things which our honorable Deganto Sengupta will be telling us in the outcoming of the forthcoming session. But in order to do this, we will be going for an explainable AI. With this heads up and with this background in the background, I please request our chairman, Mr. Dr. Nirmal Das, West Bengal State Center IEI, to give a welcome address for us. Thank you.
Thank you, Sujoy. A very, very good evening to you all. First, I would like to welcome you all in today's webinar. As per this information goes, Dr. Hemant Thakre, our President IEI, Institute of Engineers, India, Dr. G. Ranganatha, Chairman of CATE, Dr. Engineer Amit Kumar Das is Chairman of Computer Engineering Division Board, Dr. Shoibal Sarkar, Deputy Director General and State Informatics Officer, NIC, West Bengal, and the Chairman of the Computer Engineering Division of West Bengal State Center, IEI, Engineer Pranab Kumar Dev, Convener of the Computer Engineering Division Subcommittee, Dr. Raju Bosak, Honorary Secretary of West Bengal State Center. Today's speaker, Dr. Diganta Sengupta, Professor, Meghnad Shah Institute of Technology, Mr. Sujoy Bose, Sujoy Roy Chaudhary, Senior Technical Architect, Mindtree, as a moderator, past and present council members of the institution, and distinguished corporate members, ladies and gentlemen. It is indeed my great privilege and honor to be speaking here today in the webinar on Expandable AI, the Need for Trust, organized by the Computer Engineering Division of West Bengal State Center, the Institution of Engineers, India. Being the chairman of West Bengal State Center, IEI, it is my privilege to address the gathering of eminent engineers and technologists who have joined today. On this occasion, let me extend a warm welcome to you all, and especially to our panel speaker. The aim of today's webinar is to increase the understanding on the emerging and vital technology that is expandable AI, and its development as a built-in feature with AI to comply with regulations, as well as examine its applicability as an integral and fundamental part of AI-based systems to meet the demands for expandability and transparency. As we know, the increased application of AI to gain automation has grown the complexity and scalability of the system, and consequently the need for transparency, understandability, and explainability of the AI-based system. Explainable AI provides methods and techniques to provide explanation about the used AI and the decision made by it. Consequently, it helps attain human trust. Because of AI, power systems are based on probability and uncertainty, the right level of explanation is key to helping users understanding how the system works. Once users have clear mental models of the system's capabilities and limits, they can understand how and when to trust it to help accomplish their goals. A June 2020 IDC report found that business decision makers believe explainability is a critical requirement in AI. To this end, explainability has been referenced as a guidance principle for AI development at DARPA, the European Commission's high-level expert group on AI, and the National Institute of Standards and Technologies. Startups are emerging to deliver explainability as a service, like Truewords, and tech giants such as IBM, Google and Microsoft have open source both explainable AI toolkits and methods. Today, we have a very good panel speaker who has an authority in the field. Let us educate ourselves on the theme and explore how this can help us in our digital and comfort living. Let us enjoy today's webinar. Thank you and welcome you once again. Sujay.
Thank you. Thank you, Dr. Nirbal Das, for your welcoming speech. May I please request Mr. Amit Das to give a speech for us? Mr. Amit Kumar Das, Chairman, Computer Division, IEI. Hello. Oh, I think Mr. Amit Kumar Das hasn't joined our session because of a busy schedule. And also Dr. H.O. Thakre, President IEI, would be also be joining, but he is also not with us because of his schedule itself, and Mr. Sandeep Kumar Dev as well, Vice President IEI, and Dr. G. Ranganathan as well, Chairman, Committee for the Advancement of Technology and Engineering IEI. So, so they are not joining. So again, may I request Dr. Soibal Kumar Sarkar, Chairman, Computer Division Subcommittee, West Bengal State Center IEI, to have some speech. Hello. Soibal, be joined. I think Shrivalda also haven't joined. So may I directly go to Dr. Diganto Shengupto, Associate Professor, Department of Computer Science and Engineering, Meghnad Shah Institute of Technology, Kolkata, to give us, to enlighten to us on this trust-enabled AI for us. All the stage goes to the Dr. Shengupta itself. Thank you, Dr. Shengupta. All is yours now.
Hello, am I audible?
Yeah, you are audible.
Okay.
Thank you.
Thank you. Good evening, everyone. It's really my honor and my pleasure also to be sharing this stage today in this evening, discussing one of the very dear topics of mine, that is the explainable AI. I thank the Institution of Engineers for providing me with this platform. Now, such and in the inauguration itself, Mr. Roy Chaudhary and Mr. Nirmal Das has already quoted upon the requirement of artificial intelligence and the explainability of artificial intelligence. From when artificial intelligence came into picture, for example, as Mr. Roy Chaudhary said, that it was the 1950s during the famous paper of Alan Turing that artificial intelligence came into picture, and my presentation is also going to start with that itself and all the GDPR rules concerning explainable AI and all those things. So I would like to share my screen. Is the screen visible? Kindly anyone?
Yeah, it's visible.
Okay.
Please
Okay.
go. Yep.
Okay. Thank you. So explainable AI, or normally XAI, that is the short term of explainable AI, which we are using nowadays. So AI, as we see that AI is a concept that had been coined in the early 1950s itself, but due to after the advent of the high-speed processing units and the infrastructure, mainly the cloud server infrastructure, GPU architecture, and more sophisticated CMOS devices, the AI has we have witnessed that for the last 1 decade, the artificial intelligence has seen an phenomenal explosion. Okay. Now, after that, what happened in the last couple of, or rather in the last 3-4 years, explainability of the AI has become an issue. Means whatever model we are designing using artificial intelligence, we have to explain it. Now, it was not that suddenly out of somewhere the explainability issue cropped up. It was a sequence of events, as we will be seeing just now. It was a sequence of events which questioned the AI models. The AI models were good at giving us results, but there was some situations which triggered the explosion of explainable AI, which we can say. Okay. Now, what is AI? In the AI case, I would like to say that what is the difference between artificial intelligence or machine learning models and the traditional models? The traditional models were rule-based models. We learned algorithms during our early years of our bachelor's, masters also, that those were the rule-based models, and artificial intelligence or machine learning works on mainly on the data part. Means these can be termed as data-centric models. So starting with AI, I would like to just throw a small focus on AI, and after that carry on with the explainability. Okay. Now, as I said, artificial intelligence, and as Mr. Roy Chaudhary also quoted in the beginning itself, it was a seminal work of Alan Turing in which he asked, can machines think? In the 1950, in the Computing Machinery and Intelligence paper, he asked, can machine think? Can machines think? And then the famous Turing test was designed. Now, the Turing test was the measure of intelligence of a machine in answering questions with respect to humans. And till today, also, we use the Turing tests in many scenarios. So, in 1950 itself, you can see that the Turing tests were designed, which was used to measure the intelligence of a machine in answering questions with respect to humans. Now, what if the machine is answering the question? Can we understand it? Even if the machine answers a question, can we understand it? For example, at that time, there were some games being played, and suppose the rules of the games, the dictionary that the games follow, the vocabulary that the game is following, and suppose a machine gives the answer also. But can we say that it is understandable, or can we say that it is explainable? This is what we are going to look in the following slides. So, what is the need to explain? The famous in March 2016, AlphaGo defeated. Please give me one time. My panel is blocking my view. So, in March 2016, AlphaGo defeated the Korean champion Lee Sedol in the 37th move. It is also known as the legendary 37th move. Now, AlphaGo was built by Google DeepMind to play the game Go. Now, Go is a highly complex game. Now, Fan Hui was a Go champion. He looked at the 37th move and he said that it is not a human move. I have never seen such a man playing such a move. The move was brilliant but could not provide an explanation. Now, this was the time I am talking about, March 2016, when the Google DeepMind game means the player or the computer AlphaGo defeated the Korean champion Lee Sedol in the legendary 37th move. So we say, now the question arises, can we say that March 2016 as the onset of explainability? Because here, as Fan Hui has already said that it is not a human move, and I have never seen a man playing such a move. And definitely, if that move decides who is the winner, then that has to be a good move, and it was definitely a brilliant move. But it could not be explained at that time, even by the Go champion. So, can we say that the March 2016 is the onset of the questions of the explainability of AI? So going forward, let us see. This is the Google Trends Popularity Index. Max value is at 100 of the term explainable AI for one decade from 2011 till 2020. And if we look at it, it can be found in the net itself. Anyone of us can search it in the name with the key term, search term as explainable AI. Now, if we look closely, this is the time the 37th move of AlphaGo happened. So, from the data from the Google Trends itself says that the quest for explainability among the researchers or among the global computer scientists, global research community started. If we look at the trend itself, we can assume that it started after the legendary 37th move itself. Because from the graph, the red box itself shows how the quest for explainability has started. So we saw that as from 2011 till 2019. Now next, if you look at the last 5 years popularity index again from Google Trends, which max value is at 100, with the key term as explainable artificial intelligence. we see that in the last 5 years, from 2017 onwards, till date, if you can say till date yesterday, because this trend data I have taken yesterday itself. So till date from 2017, we see that explainable AI quest is almost over 25 out of a max value of 100 throughout the last 5 years. We can, if you look at the interest for explanation among the global, among the countries in our world, we see that is South Korea is leading with the highest number of searches containing explainable AI, and in this, our country is at the 21 position, and I think it is pretty not bad. It's very good at this scenario. Next, if we look again, if we change the keyword here, the key term is explainable AI. If we change the key term to explainable, it was the explainable artificial intelligence. And now if we change it to explainable AI, then we see the data as Mauritius, South Korea, and Singapore. Again, Mauritius is top heading, and India is at the 8th position. Again, it is pretty good. Since explainability, we can say that after March 2016, the quest for explainability started coming into the picture. But in the last couple of years or 3 years itself, explainability has gained momentum. People are working on it, people are designing models, people are designing frameworks. So, in that itself, the search for explainable AI using the Google itself, our Google Trends, we see that India is at the 8th position. And again, the leading two countries are the South Korea and the Singapore in both the contests. So, these are some data that I searched from the net using trends that the topic is explainable AI, and whether this topic and what is the, you can say, weightage of the topic, because soon now in the coming slides we will be talking about weightage also. What is the weightage of this topic in the current scenario in the last 5 years? So again, if we go for the explainability of the AI models, first we have to go for the AI models. Now we are using artificial intelligence or machine learning in almost all spheres of our life. Okay. Now from predicting whether a certain team will win the game or not, by predicting that tomorrow there will be rainfall or not, and everything AI is contributing heavily. But there now, suppose a person in a football game, suppose a person is going to kick a football, and we have to predict that whether that will the outcome will be a goal or not. Now that is okay. We are going to predict whether the outcome will be goal or not, and that is something that is not, means on the priority list. It will not go in such a position where the financial decisions or the healthcare decisions come into picture. So explainability of a kick of a football cannot be compared with the explainability of whether a person is going to have a stroke or not, or whether a person is going to invest a certain amount of money in, suppose, in financial services or not. So depending upon the priority of the, you can say, the application, explainability also varies, means the percentage of explainability also varies. Say for example, in kicking of a football, how much explainability we can, it's okay for us, and for predicting whether a person is going to have a stroke or not, how much explainability we need from the model. So that also gave rise to the, again, to the interest for explanation, and two sectors emerged as the leading sectors for explainability. One is the finance. Over here, if you see, it is finance. And Norway is using explainable AI, or Norway is more interested in explainable AI for finance on the global scenario. And the next one, as I said, is a healthcare. Again, healthcare, if you see the graph itself, the Google Trends graph itself, it's a lot amount of searches in healthcare domain, and it is China that is leading in the searches for the healthcare explainability of AI models. Now, in the Google Trends, if we can have the drop-down list over here in the health itself, and there are other application areas also. Agriculture is one of a very good application area, and from there we can see the trends. But after analyzing all the application areas, it will be seen that the finance and healthcare has witnessed the most number of searches in this domain. So having looked at the some of the data, and having looked at what explainability can help us in, and which domains attract or need more explainability, let us come to some explanation. Now, there was a famous project, the not famous project, there was a project going on in the 1990s, and the outcome of the project was to predict whether a person is going to die from pneumonia or not, and what are the key features, or what are the precautionary measures that could have been taken. So that was a project going on in the mid 1990s, and the outcome was very good. The outcome was means that the model gave an outcome of above 80% and nearly 90%, and okay, fine. So if there is a 90% or 80% above 80% result in the outcome, means prediction in the outcome, then it was deemed fit at those times. But the most striking thing is that the outcome, one of the outcome was asthma sufferers are less likely to die from pneumonia than the general population. Now it can be found at the link that I have given over here. Now this is what triggered the alarm. See, an AI model is predicting an outcome, but when it is asked to explain itself, when the AI, since as I said earlier, the healthcare application, the healthcare domains needs explanation very highly. So when explanation was asked from the model itself, it was seen that the model explained its outcome of say 80% or 90% accuracy by saying that asthma sufferers are less likely to die from pneumonia than the general population. Now, as human beings, by looking simply at this sentence, we can say that there is some problem going on. So in mid 1990s, the study of ML techniques for a pneumonia risk assessor, as I said earlier, University of Pittsburgh Center for Biomedical Informatics was at that place it was being conducted. So the goal was not to diagnose pneumonia; it was to figure out who are high risk or low risk patients. The neural network was the most accurate model and performed really well because eight statistical models were tried on the data set, and the best model was selected. And out of the all the eight statistical and the models, neural network models, the neural network was the best model that performed it at that time. But when asked for explanation, the neural network model said that asthma sufferers are less likely to die from pneumonia than the general population. Now, what does this explanation mean? The doctors provided that explanation. In the mid 1990s, the computers did not have so much of, we can say that explainability intelligence. So the doctors had to explain it, and the doctors provided the explanation was that the patients with asthmatic history were treated with higher priority in ICUs and therefore received early stage treatment. And the patients themselves also, since they were asthmatic for a long duration of time, they knew that when they are having the problem with respect to say normal patients. Okay, now if sometimes I have a breathing problem, I won't be knowing whether that breathing problem is risky or not, or how much is risk associated with it. With respect to a person who is having asthma, since he is having asthma, he or she is having asthma, he or she is already knowing the level of breathing problem and when should I seek for medication, which might not be the possibility for other human beings also. So as the patients themselves were highly aware when shortage of breath started. So what happened if there is a shortage of breath started? The patients themselves went to the hospital. In the hospital also, while filling out the form or while in the preliminary diagnosis level, the doctors came to know about that these are asthmatic patients, and they were treated accordingly with an early stage treatment in the ICU. So what happened? The data which had different types of patients, among them, all those asthmatic patients received early stage treatment in the ICUs, and also those patients came to the hospital, you can say in the before the golden hour or in the golden hour itself. So they were saved. Now, this explanation, which is provided by the doctors, was not taken into account by the model. The model did pretty well. The model did pretty well on the data set and said and gave the predictions. But see where in the healthcare domain where the problem lies, the model thinks all those patients who are having asthma are less likely to die from pneumonia. Now again, this was a means the caution for explanation, since it was a healthcare domain and in the 1990s it was discussed upon in the project itself. So the model was never deployed at that time. Another explanation. Vision needs explanation. Out of here, if you see, we have 10 images. Okay, and for the sake of simplicity, I have taken 10 images, but it was executed on multiple number of images. And this is also a famous experiment. So it was to predict whether the objective of the AI model was to predict whether the given image is that of a wolf or that of husky. Okay. Now, in out of these all these predictions, you will see that there are only two errors. If we say that there are 10 predictions, we can see that there are two errors. The in the red boxes, I have marked it in the slide. In the first one, it predicted husky, and actually it was wolf. And the second one, it predicted wolf, and actually it was husky. Okay, now out of 10, if you see that there are two prediction errors, that means there are 8 correct predictions. Again, the accuracy is 80%, right? And when the model was run on a bigger data set with multiple number of epochs, it was observed that the accuracy also reached 90%. Now, 90% accuracy or 80% accuracy in predicting whether the image, or suppose there is a live feed from a camera in suppose in a park or a jungle or anything, from there the image is coming, and then the image is fed to the model, and it predicts that whether it is a wolf or whether it is husky with 80% and above accuracy. So it is good, pretty good, no issues. Then we can say that the model is definitely a very good model, and that it is giving very good results. But again, some people started for explanations. It was this experiment was conducted in 2018, and can everyday AI be ethical? Why it is called every the paper in the paper it was beautifully written that everyday AI in 2018, as I said, it's about 4 years earlier. So in the last 5 years itself, AI has penetrated in almost every sphere of our life, from the wearables that the smartwatches or the wearables that we wear, to our this chatbots, simple Siri, Alexa, and all these things. So can everyday AI be ethical and believable? So 80%, as I said, 80% prediction for whether an image is of that of a wolf or a husky. But when explanation was asked, when the model asked for explanation, we observed that the model was predicting whether it is a wolf or a husky depending upon the snow part. In the right side of the image, if you see, there are the white markings. It was not even taking into consideration the face of the animal. What we as human beings think, that if there is an animal, or if there is an animal, be it a wolf or a husky, we will be looking at, or at least our intelligence looks at the structure of the face, the eyes, the nose, the ears, means if the whole picture is there, how it is standing and how it is running and all those things. The AI model was giving above 80% accuracy by looking at whether there was snow in the image or not. Now, this was another alarming situation. The model was giving 80% above accuracy, but the model was predicting and giving the result based on snow, not even the face or the type of animal or any other feature or any other quality, or not quality, feature of the parameter or feature of the face that it should have been. Means when we are designing the models, we think that these parameters will be taken into account, these features will be taken into account while designing a good model, while designing, or rather while predicting or coming to a conclusion or decision. But again, in the black box, what I am terming as black box is the AI model. The input is coming and the output, we get the output. What is happening, we did not know earlier. Only when explainability came into the picture, we came to know that, okay, inside the black box, the outcome is based on snow, not on the actual features of the face. So these are two explanations. So explanation reveals how the black boxes are working. So they help us in improvising the model. So once the engineers came to know, or once the computer scientists came to know that, okay, this model is basically predicting based on the snow, now they rectified the model. They again fine-tuned and rectified the model so that now the model will be working on the features itself rather than the unnecessary features. So they help in improvising the model also. So this is one of the good users of explainable AI. So when we have the explanation, we can know that, okay, if the model goes wrong, then also we know that where the model went wrong, and if the model goes correct, then also we know that on what features did the model give us the correct results. So, but there is a word of caution associated with it. Let's see another example. Now, this is an interesting example. This, as I said it in the last slide, a word of caution. Why a word of caution? Once we come to know about which features are important, or depending upon what, from the image, depending upon what areas or what features or what parameters our model is deciding, there can be reverse engineering. See, for example, in this experiment that was done in 2015 itself, this is the model is predicting this as a king penguin. It is predicting this second red box as a baseball, the third one as an electric guitar, fourth one as a peacock, this one as a cheetah. Now, and that has been done with greater than 99.6% accuracy, greater than equal to 99.6% accuracy. So a model is correct. It is correct to the extent that out of every 100 occasions, almost 99.6% times, the model is giving correct results. But internally, we see that these are the things which classify whom the models classifies as penguin, baseball, guitar, peacock, and cheetah. As human beings, we understand that absolutely this is not correct. But the computer model, the AI model is deeming these as correct. So what happened in this picture? Explanation provide insights on feature importance. When we start having the explanations, we know which features are important, which thing and which thing are. Now, if someone wants to reverse engineer it, in the previous example for the husky and the wolf, if someone knows that this model is working like this and he wants to attack that model, there can be malicious attack. If he or she wants to attack that model, he can use some images, build some images with only those parameters on which the model is concentrating. So these are the outcomes. These 5 boxes, or rather these 16 snapshots that I have given, these are the in the slide. These are the outcome. So once you are having the features on which, and you know that these are the features on which the model is performing, or on which the model is working, you can use those features to generate cases in which the model will say it is correct. And see, our model is also saying correct 99 over 99.6% of the times. So these are some interesting areas on which which triggered the quest for explainability in the AI models, artificially intelligent models. And after that, since there were these were triggering questions, and since, as I said earlier, the financial and the healthcare applications of AI are very crucial. So, as in the beginning of the today's session, also Mr. Nirmal Das also pointed out this uh, European Union mandating the GDPR of AI. So I have included this slide also, and it matched with what he has said, that European Union has all mandated explainability and monitoring in the proposed GDPR of AI. Okay. Now, what European Union has said, that you are having the data, your model is using the data. The data is being used by the model, so you have to say how the data is used and uh, how you are working on the data, how the data is used, and what results are coming out when you are working on the data, and how you are working on the data. So they came up with the AI system classification. They made 4 classes of AI systems or AI models that normally people are building into minimal risk, limited risk, high risk, and unacceptable risk. So behavioral manipulation models have been banned. Okay. Now, second, high risk models are the autonomous cars, the credit scoring, all these things, credit scoring in a bank. These has been termed as high risk. Transparency obligation are the chatbots. They are limited risk, and the minimal risk are the spam filters. Okay. Now, suppose I go to a bank, I apply for loan, and the person sitting over there straight away says, "No, sir, won't get it." If he says you will get it, we won't question any further. Normally, being human beings, we don't question if we get what we want. But suppose he or she says that no, sir, you won't be getting a loan. Now, the very first question that I will ask is why. Now, this why itself is the trigger word for the explainability of the AI model. Now, if that person is saying me no based on some AI model, then he needs to explain it to me why he is saying no. Then he needs to the model also to explain it to him why the model is saying that no, this person cannot be given a loan. So in the finance sector and the healthcare sector, as we have seen earlier itself, again, these are high risk applications of the AI systems. So there are 3 critical topics within the guidelines for high-risk AI systems. Just I will go through this: the transparency, monitoring, and the record keeping. The user should be able to understand and control how the AI system outputs are produced. And high risk and the rest two are regarding the high-risk AI systems. So they should perform consistently. This word consistently, we will see in the following slides that what is the importance of this word consistently throughout the life cycle and meet a high level of accuracy, robustness, and security. And throughout the life cycle, and the record keeping, that enabling the automatic keeping of records, that they are logged whatever they are doing, or however the data is being processed, number of epochs that your neural network is executing, the amount of data that is being fed, everything should be having a log. I mean, a log should be kept for everything. So these are the three critical topics within the guidelines of the high-risk AI systems. Now, suppose I want to build an AI model, and that model I want to be in the say society applications and other things in GDPR. Now, then I have to go, or a person has to go through the complete GDPR, and then he has to assess that whether the model is acceptable or not acceptable, or rather whether the research is publishable or not publishable. So in this context itself, there is a there are lots of legalities that we have to face, not only doing research or not only the person who are building the AI models, but they have to also know about the legal issues of their AI model also. So there are lots of legalities. Now, this paper in 2022 February, this year February itself, this paper has tried to bridge the gap between the AI and the hello. So this paper itself has proposed a research in which the authors tried to bridge the gap between the AI and the explainability in the GDPR towards trustworthiness by design in automated design making. Now, the authors studied the challenges of providing human understandable explanations for AI-based decision making systems in practice. And they came up with 2 points. They used this GDPR of AI and the AI modeling into two dimensions. One was automated decision making in credit scoring risk, that is a finance sector, and the other was the other one was in the medical diagnosis of COVID-19. And the conclusions were
Can everyone go on mute, please? Hello. Can everyone go, or can you make everyone as mute except Dr. Dibant Sengupta? Yeah, yeah. Dr. Sengupta, you can go ahead.
oh, thank you. So as I was saying, in this paper, they worked on the two important domains. One was the finance domain and other was the healthcare domain. Now, the conclusions that they came out, the conclusions of this research in this year, February itself, current machine learning techniques, in particular those based on deep learning, are unable to make clear causal links between input data and final decisions. Causal links, this is important because in our this slide itself, today's talk itself, we will see the causality also. Okay, the difference, the importance of causality also. So current machine learning techniques are unable to, mainly deep learning is unable to make the causal links clear. The quality of explanations might not be considered as adequate safeguard for automatic decision making under the current GDPR. Okay. And additional tools such as algorithmic impact assessment, other forms of algorithmic justifications, broader AI principles, and new developments in trustworthy AI should be considered to complement explanations. So these are right now, if we bring AI in one hand and the GDPR into another hand, and we want to make trustworthy AI, then we have to go and abide by these rules with some exceptions as given in the conclusions itself. And those exceptions will also have to be carried out in by either developing new technical developments, technological advancements, or designing some algorithms. Or in case of healthcare, also we can say that by having the results tested or verified by a team of doctors, specialized and physicians from that domain itself. So we know the term explained by this time. Okay. So by this time, we know the term explainable AI. Now I have pointed out XAI, as I said earlier also. We need the need for Xi. Okay. For the last few times, we have already seen the need for Xi, why we need Xi. Global interest in Xi region wise, in what is the global interest in that Xi is coming up in searching.
Hi everyone, can you please go on mute? Everyone, can you please go on mute? It's quite annoying.
Okay.
Yeah, please go ahead. Sorry for this.
No,
But
no.
that's
So till now, again, I'll repeat this. So till now, from the beginning of today's evening in this topic, we have seen that the term explainable AI. We have been seen what is the need for Xi. We have seen globally which regions or which countries are more searching for Xi or explainable artificial intelligence or explainable AI. We have seen some interesting. We have
Admin, can you please mute the
We have also seen the GDPR of AI, GDPR of AI as mandated by the European Union. We have seen how the GDPR and the explainability gap can be resolved, and what are the areas that we have to focus on mainly. Now, out of the last few slides, since the beginning of it, we can say that the Xi model should be fast. Our Xi model should be fast. F for fair, accountable, secure, and transparent. So these four terms can be said regarding the foundation of the Xi models. So let's dig a bit deeper now. We have seen what is Xi and why we need Xi. What is the global vision or global focus on Xi and all those things. Now let's dig deeper in the technicalities. So suppose we are having a simple classification. We want to do a simple classification model between the height and weight of a person. And these are the data inputs that we are having. Now by using any sort of, we can go for a linear regression model. Now this is the regression model and this is the hypothesis that we draw. Now going by this, we can say that, say, suppose this is a new data point. Now looking at the model and the hypothesis, we can say that for a certain weight W, the height will be h, and it is pretty simple. Okay, so it is a simple linear model and it has a very easy explanation. Now let us see if the model becomes a bit complex. Now this is a bit complex model which needs classification. And again over here we see the hypothesis, the green dashed lines, the curve. And now if we say that the new data point is over here, now explainability will become an issue over here, right? Because it is no more a linear and it is no more easy. So what happens? The explainability in this case, in these type of scenarios, depend upon the red dashed box that I have given. Okay. Now in the previous example, the explainability in the linear model, the explainability was depending upon the whole model, whole data set, whole representation itself we saw. But in this case, if we take into account the whole representation, explainability will become tough. So what happens in this case? We use a small part, a small segment to provide explanation. This is known as local explanation, and the previous one was known as global explanation. We will see into it just now within a few minutes itself. So this is the main thing where in this is basically the local explanation. Now going forward, so no more it is a simple model. It is tough to explain taking all the data points. So what we do, we explain it locally. As complexity, so we can say that as complexity increases, explainability decreases with respect to the global model, not the local part. If we take into account the global model, all the data points, then we can say that as complexity increases, explainability decreases. So from here, we can see this diagram of between the accuracy and the explainability. Okay, highly accurate models are the non-linear models, non-smooth relationship, long computation time. Those are the neural network random forest support vector machines, graphical models, and the highly interpretable models or explainable models are linear and smooth relationships, easy to compute. So you see over this diagram itself, as the explainability increases, if we want more explainability, then accuracy is going down as of now in the present technological situation. Okay, and it is also a myth also. The myth is there and it is a fact also. It is a balance between a myth and a fact. So if you look at this diagram, what happens? If we want to increase the explainability of say a neural network, okay, by going by this diagram, these are the machine learning models, standard machine learning model neural networks that we use. So by going by this diagram, neural networks we can see over here has the highest accuracy. but least explainability. So if you want to increase the explainability, and if you believe that the machine learning models will be along this curve itself, then we can do this, right? If we do this, then what happens? Now, if you look at the neural network, random forest, and support vector machine, the explainability has increased without any compromise on the accuracy. And right now, majority of the research, majority of the global research is going on in increasing the explainability of the neural networks, random forest, and all the high-end models without compromising on losing on accuracy. So, if we can do like this, then the myth doesn't continue. The myth that explainability and accuracy are inversely proportional doesn't come in this also. It continues. This also it is valid. But what happens now? We have increased the explainability also, and this is what the recent designers, the researchers, the model, those people who are building the models and the framework are looking into. So explainability increases, explainability increases, preserving the accuracy. So how to explain now? Zai. AI models, input comes, we get the output, and in the middle there is a AI model. Now, those AI models are normally termed as a black box. Okay. But there are some models which we can see also, as we saw in the linear regression case in the previous example, that we can explain it as we are going itself. So those models are known as white box models. Those are the explainable by design models. By design, by inherent design, they are explainable. And there are some explainable black boxes. Definitely the neural networks and all those machine learning models in the upper part with higher accuracy were the explainable black box models. So these are intrinsically explainable models, interpretable models, white box models. For example, the linear regression, logistic regression, decision tree. These are white box models and they can be explained by design itself. They are intrinsically explainable. They are intrinsically explainable. Okay. Next, so for designing whiteboard models, there are 4 rules. The handcrafted expert systems can be designed. Case-based learning systems can be used for designing the white box models. Rule-based systems can be used for designing the white box models. And there can be embedded symbols and extraction systems which can be designed for designing the whiteboard models so that it can be explained inherently or intrinsically. Okay. Now, in case-based learning, they make use of examples, cases, precedents, and ensure the outputs. In the rule-based, there are algorithms and logical rules written for data. And for embedded, this is more of a neuro-symbolic computing, more biology-inspired, bio-inspired compute algorithms are used. Okay. So we explain while we build the model in white box, as it was written that explainable by design. That means we explain while we build the model. What if the model is already built? In every scenario, it is not that we get the problem statement, we get the data, and then we start building the model. It may happen that we get the problem statement, we get the data, and there is an pre-existing model on which we can feed it and tune the model and get the output. In most of the cases also, we use that and it's a big part of the transfer learning process also. So what if the models is already built? So explaining black box models, there are 3 important things that are needed to be looked into for explaining the black box models. The first one is the properties of the models, identifying feature contribution and the bias components. The second one is local logic, looking into the logic of each single decision and going for explanations for an individual prediction. Individual, as the diagram in which there was a bit complex curve earlier in the height and weight example. We use for local explanation. The explanation for an individual prediction, a small box in individual prediction, we look for it. And if you are looking into the complete model, then it is known as a global logic. So we can say that explainable AI can be broken up into 2 parts, that is the white box and the explainable black box. Black box comprises of the global logic, local logic, and the model properties, and accuracy increases. The explainability increases like this. White boxes are the most explainable, and the black boxes explainability increases according to the black boxes, depending upon the model properties, the local logic, and the global logic. Next, we come to the post hoc explanation. This post hoc explanation is basically depending upon the model, the scenario where the model is already built, as we were discussing in the last slide itself. Either we build the model or there is some pre-existing model. So there is an AI model which has already been created. Now we are going to explain it. So that scenario is known as a post hoc explanation. Explanations are generated with an existing model. So there are two types of model type. Suppose we are given a model, there can be two types. Either we know the specific what model has been given to us, or we don't know what model has been given to us. So in that case, it becomes any model. Okay. So there are two types of models in existing models. Now, if there is any model which we have to explain, the approach is model agnostic explanation. And if there is a specific model we have to explain, then the approach is model specific explanation. So these are the two differences. See, suppose I have a problem statement, I have a data set, and I want to implement and see some classification or prediction rules, prediction outcomes. Then the system which is coming to me, either I know which system is coming or I don't know which system is coming. So if I know which system is coming to me, which black box is coming to me, then it is a model specific explanation that I have to do to explain the model. And if I don't know which black box is coming to me, then it will be a model agnostic explanation that I have to do for that model. So the picture is something like this. We have the learned function, then we have the model types in post hoc, agnostic, specific, or intrinsic. In specific model, it can be intrinsic also. If we have a specific model that is suppose linear regression, then decision tree, then or it comes under the intrinsic part. So the model type can be either agnostic or specific, and explainability can be either local and global. And after that, the results can be interpretable or explainable. In the previous few slides, also somewhere I had used the word interpretable and explainable interchangeably. I had used the word interpretable and explainable interchangeably. And what is the difference? We will see down the line. Okay, they are not both are not same. There is a big difference. But we, as of now, let us assume that both are can be used exchanged for each other. But the difference we will also discuss in today's session itself. So we see after we feed the learned function. After we feed the learned function, the model type is decided, and after that, the explainability comes into the picture. And then the depending upon the local or global explanation, and after that, we either interpret or explain it. And then the human beings are analyzing the results. So in this picture, this is the explainable human interface. Starting from the model type till the results come to the human being, starting from the model type till the results come to the human being, this is the explainable human interface. And this is a Xi main flow. From the learned function to the human being, this is a Xi main flow. Now, properties of local or individual explanations. There are 4 properties of local and individual explanations. One, they have to be accurate, standard ML accuracy, but from the Xi point of view. They have to be consistent. If you remember in the starting phase of our discussion today itself, we had I had pointed out a word consistency. It was written earlier also. Now, the consistency is the similarities between explanations from different models on the same task. The problem statement is same. Now different models are working on the problem statement, and the similarity between explanation, and we are explaining the different models also. Now similarity between explanations of the different models trained on the same task is consistency in the Xi terminology. Stability is another part. Explanation between similar instances of a specific model. In consistency, different models are there. Similarity between explanations. In stability, single model is there. Similarity between different instances, that is stability. And comprehensibility is one of the most important part. How well humans can understand the explanations. How well humans can understand the explanation. For this comprehensibility part, I'll discuss with an example. For example, suppose a fish says, let me go to the bank. And suppose fish could speak. Let us assume the fish can speak. Means fish definitely, let us assume the fish is having a vocabulary, it is having a dictionary. And like us, as we speak in English, Bengali, Hindi, multiple other languages, fish also has some language. And it is saying, let me go to the bank. It is speaking. It is saying, let me go to the bank. Now, do we, as human beings, see, the model has interpreted what the fish is speaking. The model has interpreted. I am giving a hint between the difference between interpretable and explainable here itself. The model has interpreted what the fish is saying, and it has given me the result. Let me go to the bank. But can it explain to the human being what the fish means by it? If I think that the fish by saying, let me go to the bank means it is going to the bank of the river. Then again, if the currency is saying, let me go to the bank, suppose the currency can also speak. Suppose the currency can also speak. The model is again interpreting what the currency has said, and it is giving me, let me go to the bank. Now, these two are interpretable, but they are not explainable because of the different worlds that we live in. Humans live in a different world, fish lives in a different world, currency live in a different world. So all the AI model is interpreting all the what they are speaking, but it is not explainable. So until and unless the human beings start understanding it, we say the model is interpretable. The model is not explainable. Only when after the interpretation, what they are saying, the human beings get to understand the meaning. Then, means see, as a human being, after looking at these two examples, now I understand what is the meaning of a bank. And now I analyze it. But the model has to give it this, not the human being. Over here also, after interpretability, after interpretation, the human intelligence is coming into picture, and the human is explaining the meaning of these two lines. The model could not explain the meaning of these two lines. So this is comprehensibility, how well humans can understand the explanations. Next. So now we have raised a further question. What is the difference between interpretability and explainability? Sorry, I just mentioned it all before going through the slide. Okay. So we have discussed what is the difference between interpretability and explainability. We will see at the details later in today's evening session itself. Now, these five are the properties of global explanations: completeness, expressive power, translucency, portability, algorithmic complexity. Okay. So these five are should be taken into account while while we are designing AI models for global explanations. Now let us play a game of football. Suppose we want to predict the outcome of a football match for Team A. Okay. So very first question comes to our mind is, who are the players in Team A? Suppose we have to predict the outcome of football match. The very first question that comes to our mind is, who are the players in Team A? First, we will analyze the importance of each player. We will analyze the player importance. Second, we will analyze the player contribution. That can be, we are expecting in this game, based on the previous contributions also we can do that. Then we can shuffle the players also by analyzing the player correlation among them. Say, for example, player number 2, when he is playing center back, he might need the player number 4. He plays more well when player number 4 is at the right wing and player number 8 is on the left wing. So these are the correlations that we have to see also. Okay. Now suppose we have by shuffling the player also, now we shuffle it. We bring player number 8 at the center back. We send player number 2 as a right wing on all these things also. We have to take into account if you want to predict. These are some small steps that we do. There is a plethora of steps that go into account while designing the model. This is just for example, a toy example. Okay. We calculate the weightage of each player in the team depending upon how much he can run at a stress, which position he plays better, what are the correlations and all these things. The previous 2-3 points and all these things we take into account. We calculate the weightage of each player in a team. From weightage, we calculate the most important players in the team. From weightage, we calculate the most important players in the team and then focus on those players who have the maximum cumulative weightage. Suppose there is a team of 18, out of which I have to select only a team of 11. Okay, now normally there are some people who are kept, there is a total team, and out of that we have to select a subset of team to make subset of players to make a team. So what we do, we calculate the weightage and all this contribution, shuffling all this thing for all the 18 players, and from there, depending on the maximum cumulative weightage, we will take the top 11 player. This is normally what means the normal logic comes into making the picture. So this is how the decisions, or rather the points which are to be included for making the decision, is done. It is a toy example. Then we try to predict the results focusing on these players only. So after that, after that, we can predict that what will be the outcome of the football match for Team A. Now, let's try to predict survival chances of a person having fatty liver using a non-alcohol fatty liver disease. And the dataset taken from Kaggle. We have done work on this dataset. We will see just now. So we are trying to predict the survival chances of a person having a fatty liver. Okay. So this process that we discussed in the whole slide remains the same. Just the football is changed by life, and all the players are changed by features. Features mean the properties or the parameters. Features means the parameters. So very first thing what we do, what are the features in the data set? We will analyze the importance of each feature. We go for feature importance, then we go for feature contribution. See, now what happens, earlier we were discussing on the football game, now we are discussing purely technically according to the dataset and the AI modeling part. And this is the steps of modeling which we require for the explaining the AI model also. So after feature importance, we see the feature contribution, then we shuffle the features and see the feature correlations. We see the feature weightages, and from there the important features are selected with the maximum cumulative weightage for all the features. Then we try to predict the results focusing on these features only, the 11 features, if we go according to the according to the game of football. So this is how the explainability in case of football game, or predicting if team A is going to win or not, or in case of a human life, for predicting if a person is going to live or not, if he or she is having a fatty liver. Okay. So the first, this red box that I have given on the point number 3, it is permutation importance. This is termed as permutation importance in general explainable AI terminology. Okay. The second one is known as partial dependency plot. The shuffling, the correlation between multiple features, 2 or 3 features, these are known as partial dependency plot. Permutation importance. These are important for analyzing the, or rather explaining the AI model. These are some technical terms. So now let us come to the model agnostic AI. There are two most popular models that we use, that is a LIME and the SHAP, the local interpretable model agnostic explanation. It was proposed in the seminal work, Why Should I Trust You? And the details can be found in the GitHub link I have given over here. And the other one is SHAP, it's the Shapley additive explanations, a game theory approach. And basically the Shapley value is calculated and taken into account. And it was first proposed by Lord Shapley in 1951. And it's for the cooperative games. Now, I will not go into the technical details of these methods and all the other methods also, because it will take much more time and much rather than what I have been allotted. So I will be viewing on what Lime can do, what SHAP can do, and what are the other models that people can use, what are the already available libraries in Python that we can use for explanation. But normally model agnostic Xi is addressed using Lime and SHAP in most of the cases. So again, the question will arise, if there are two methods in which we can do, then where to use which. So in this case, Lime's explanation for a single prediction is more interpretable than SHAP's. Both can aid in the single prediction, local explainability, but SHAP can be used for global explanation also. In local explainability, it is model dependent. Okay, but again, Lime performs faster than SHAP. And so for local explainability, normally we prefer Lime. For global explainability, we prefer SHAP. And what is local and global explainability, we have discussed earlier today itself in this session itself. Okay, so if there is a confusion, you are having a problem statement, you are having a data, and then you start deciding on which model to use and how to explain it. If you see that the complexity is high and you might have to go for local explainability, first choice is Lime. Let us see what happens if then SHAP. And if we know that we can go easily for the global explainability, SHAP will be our preferred choice. Now, these are some of the GitHub libraries for Xi, IBM AI Explainability 360, Interpret ML, Line, SHAP, and TensorFlow libraries, dependency plots, LE5. We have used LE5 in the one we will discuss right now itself. iModels, Captum, Alibi Explain, Akitas, DeepViz Toolbox, Omni Xi, and Shapash. Till now, till date, in the last 2-3 years or 4 years, whatever model and framework has been built and GitHub libraries have been provided for explainable AI, these are mentioned over here. Now, this is the taxonomy of the interpretive ML interpretability as I've seen in the last. So whatever we have discussed till now, we would like to put it in a taxonomy. So this taxonomy was proposed in this paper in the last year itself, in 2021 itself. And going by this, suppose we are having a problem statement and we are having a data set. We acquire the data set and then we start thinking. After we have the problem statement and the data set, we start thinking how to address it. Earlier, while designing AI models, we directly went for the modeling of it for the better accuracy and better performance parameters, performance metrics. But now having explainability come into the picture, we cannot go for directly for the models or selection of the models. We also have to take into account whether this model that I am selecting, whether I can explain it or not, and even if I can explain it, to what percentage I can explain it, what is the application area, whether it is a high risk area or a low risk area, all these things have to be taken into account, and whether I am going to build the model or whether I am taking into account any other existing black box and working on that model. All these things, as we have discussed in the last few slides, we have to take in account. Okay. So the very first thing is the model specific or model agnostic. Means when we are going to design it, we have to first decide whether the design that we are going to do, it is model specific or model agnostic. Next, we have to see whether the data, what type of data is there, tabular, text, image, graph, what type of data, what are the data types on which we are working. Right now, these four data types are being considered for explainable AI. Next, whether we can explain it locally or globally. Next, we can, after going for the design or after finalizing on whether it will be model specific or agnostic, after looking into the data type or whether it is a single data or a multimodal data, it can happen that we are having a multimodal data also. We decide whether we will go for the local explanation or the global explanation. After deciding, then we see what is the purpose of our explanation or the interpretability. Create the white box or interpret, examine, explain the black box, complex models, enhance fairness of a model or the sensitivity of predictions. For example, suppose, as I said earlier also, whether the person, the footballer, is going to kick the ball and the ball is going to go into the goal or not, that can be equated equally. The risk factor for that equation or the outcome cannot be said equal to the person, whether a person is going to have a cardiac arrest or not. So that sensitivity has also to be taken into the predictions. So this is the taxonomy of the model interpretability. Now let us look into some hands-on. Okay, I'll just stop sharing and I will share another. Please give me a moment. This is reconnecting. Okay, I have shared this Google Colab screen. Can anyone say whether it is visible or not? Is anyone?
Yeah, it's visible.
Okay, okay, thank you. Thank you. So, has it been connected? Yes, it has been connected. So in this, what we are doing is that we will be taking the famous example that we saw earlier in the evening about the wolf and the husky example. Okay, and we will see whether, see, that was an erroneous, but right now the explainable AI library that we are having, what is the present status and whether that is explaining it correctly or not. So we have taken a wolf picture from the internet, simple internet, and then we have run it. I will not be running this part. Say, if you can see my mouse, it has been run just about half an hour earlier. I won't be running it because again, it will be consuming a huge amount of time. So, okay, let me see whether it, we start with importing the, okay. See, this is the wolf picture that we have taken from the internet. Okay. Yes. Let us assume this is a wolf. And then we import the GradCam algorithm. Let's build the, and we have used the ImageNet for our classification training purpose. Okay, the ImageNet library. Those of you who are conversant with the ImageNet, you will be knowing, conversant with AI modeling, deep learning, will be knowing about ImageNet. See, the wolf picture that we saw earlier, this picture, in this whole picture, the model is now the GradCam model has been used, and from there we see that this part, the yellow, green, and the blue part, this part is used for explaining the result that it is going to give. Means in over here it is saying that that is a wolf. Okay, Now, for saying whether it is a wolf or not, is the model looking at the snow or the model is looking at something else? So this part out of this whole blue, this part, the yellow, green, and light blue part, this part, the model is looking at this part to classify whether that is a wolf or not. Okay, so this is the explainability part that has come into picture. Now let us see. See, this part has been taken into account by GradCam to say that this is a wolf. This part has been taken into account by GradCam. Clear? So now you can see that snow is not been taken into account as was the case in 2018. In 2018, the first when the alarm was the bell was rung, whether because the snow was been taken into account by the model to predict whether that was husky or wolf. Right now we are looking over here itself that the model, the GradCam is taking into account this part, this whole part in the yellow, greenish yellow part to decide and make the prediction whether it is a wolf or not. So there are these cats and these two also. So I will not take any more time in these. Rather, this is the next one. As I said earlier, the fatty liver in the morning, in the earlier part of the session itself, we were discussing on the fatty liver part. Now let me see whether the SVM has concluded or not. Yes, it has completed. So we took the a very for this today's session itself. We went for a small data set and we did the for the sake of explainability, because more the number of features in this example itself, it took very time for the SVM model to run. So I won't be running this model now, right now. This has been run about half an hour earlier. So we had only a few amount of features: the age, male, weight, height, BMI, a few time and status. These were the feature in the Kaggle dataset. We drew the feature from the we did drew the dataset from the open source dataset library. We can Kaggle, many people know about it, and it was on the Creative Commons CC BY 4.0 license. So we are using it over here. So if you look over here, the initial dataset had 17,549 rows and 7 columns. Okay, but there were total null values. There were huge amount of null values in this CL. You can see that the number of null values in height was 4786, in weight, height 3168, BMI 4961, and so on. So the bit amount of data pre-processing was done, and these were deleted. The null values were addressed, and after that, our dataset comprised of 12,588 data points. It is also pretty much good for this type of explanations. So after that, we imported the libraries and all those things. First, we go for the decision tree classifier. When we went for the decision tree classifier, we saw these are the prediction results. We got a 0.92, means 92% accuracy. Okay. Using the decision tree classifier, we had a 92% accuracy in deciding whether a person will be surviving or will die, depending upon his fatty liver and other features, as seen over here. These are the standard RUC AUC curves. This is for SVM, support vector version. Earlier it was for the decision tree. This is for SVM. This is the ROC curve. Now in SVM, we see that there is a training accuracy of 99.99% and a test accuracy of 92.8%, 92.08%. In decision tree, it was 92%. Over here, it is 99.9 and the test accuracy is 92.8. We go for the confusion matrix ROC and then we come for the XGBoost model. In the XGBM itself, we train it and we get a 91.6% accuracy. So over here, we see that XGBoost model had given the lowest number of accuracy out of these three models. But why did we go for XGBoost? Now, after using the SHAP and the LE5, see, this is what it is giving us. Okay. We saw that the age and the FUTIME were the highest, were the most important features. They were the most important features in the dataset, or rather, they had the most weightage in the outcome, final outcome, or the prediction outcome. Here, so the age and the runtime were taken in account. If you look into it, the weightage is 0.117 plus minus. These are the issues. So from here, we get to know about that. Okay, we fed the data set to see whether a person is going to live or not live. So in that scenario, we have a result. Now, what are the features those contributed more to this result? As the football game example that I had given earlier. Okay, so from here we get it. Now this is the decision tree explanation that has been provided. This diagram is the complete decision tree, how it is taken into account. After that, these are the values. In this one, we get a complete SVM. This is the explanation of the SVM. This was the explanation of the decision tree. In SVM, we see these are the importances, and after that, we go for the contribution. Okay, in the feature contribution, we see that this height has a 21.42% contribution. This FU time has a 14.602 contribution in the predicted results. So these are the SHAP results. Over here, you see that feature 0, feature 1, 0 to 5 is basically over here. I was just coding. So these have been done by my scholars. So we have not mapped these features with the actual this thing. Means, parameter name. Okay. So feature 1 to feature 0 to feature 5 means the 6 parameter that we saw earlier. That is a height, few time, BMI, weight, age, and all these things. So for class 0 is class 0 and 1 are the survival positive or survival negatives. So we see by the SHAP summary plot that this is the outcome. So this is how it is explaining step by step that okay, these parameters had the importance in your decision. Within this parameter had the importance for saying that this person is going to live, or this parameter has this much amount of weightage in saying that this person is not going to live. Now, again, going, this is the and this is a SHAP value for the XGBoost. So by using the LE5, as I have seen earlier, I had shown earlier in the PPT, there are a multiple number of GitHub libraries in Python that can be used for the explainability. In these two example, in the Wolf example, my scholar had done the GradCam, and over here in this example, we have used the SHAP itself, and we have run three models: the decision tree, the SVM, and the XGBoost. And we saw that XGBoost is having the lowest frequency out of all those three, but explainability of XGBoost is very high. Now, why again this cannot be covered in today's session? Okay, but in out of these three, XGBoost has the highest explainability. Now let me again stop sharing. I'll go back to the PPT. Okay, so the PPT is visible, I think. Hello.
Yes, it's visible.
Okay, thank you. So, okay, okay. So next, as I said earlier, the explainability versus interpretability. As we saw in an example also earlier, but I told that we will look into it into more detail later in the slide. So here what we say, we will look into the explainability and the interpretability. So if a horse can speak, then also we would not understand it. As a fish spoke in the previous example, as a currency 100 rupee coin spoke in the previous example, we could not understand it. So the fish and the currency example. So correlation and causation in the beginning, in earlier time in today's evening talk itself, I had spoken about the consistency and causation also. So there is a big difference between correlation and causation that has to be taken into account to understand this interpretability and explainability difference. Correlation is a statistical tool to check the connection between two or more items to evaluate their coupling. Correlation is a statistical tool to check the connection between two or more items to evaluate their coupling. Causation implies that one variable caused the change in the other. One thing that makes the other thing to happen. For example, the boiling water example. It is interpretable but not explainable. Clear why it is interpretable and not explainable? Because suppose by the changing of the passing of the time, there is the heat is given and the temperature of the boiling water is changing. So if we feed it to a AI model, it will say that, say for example, at this amount of time, at this point of time, it is 80 degrees centigrade. At this point, 90 degree, 100 degree, 110 degree, 120 degree, and so on. It is interpreting the result, and it will say us also. But we know by the simple chemistry, that it is the changing state of matter that is taken into account in the boiling water example. That means after 100 degree, it is evaporating. No more picture of 110 degree and 120 degree. And that is explainability that is not required. So the boiling, while if you ask an AI model to interpret the temperature with respect to the passage of time, it will be able to interpret it, but it will not be able to explain it because there is a causal effect, and that causal effect is a changing state of matter that is a global phenomenon. So interpretability, how ML systems predict temperature change with passing time, that is interpretability. Explainability, the model should take into account the changing state of matter, which is a global phenomenon. So here I rather give you the example and in the writing itself that interpret the difference in interpretability and explainability is that for explainability we have to take into account the changing state of matter for this boiling water example and the global phenomenon also. So this is the basic difference between interpretability and explainability. And in this book by Explainable AI with Python, this was published in 2021 by Chifan and Seco. These are the differences between interpretability and explainability in these 6 points, which is the most important features that are adopted to generate the prediction or classification can be said by both the parts. That's why if you remember in one of the previous slides, in the flow, in the Xi main flow, I had written explainable and interpretable both, and I had said at that time that later we will discuss because features important selection both can do. How much output depends in the small change in the input, both can do. Correct? As we have seen earlier also, model rely on a good range of data to select the most important feature, both can do. Adopted, the criteria adopted for the decision, both can do. Now, how will the output change if some unseen data is given? Interpretability will not be able to do explainability because that picture comes from the global phenomenon. You have to understand the underlying reasons, underlying causes behind it. It's a causal effect, not a correlated effect. What will happen to the output if some features of the data had not occurred? Again, that is a causal effect and that is not a correlated effect. So we can at the foundation level, we can also say that explainability and interpretability can be thought of something that is generated from the causal effect. So I was given time till 8:30 and it is 8:29 right now. So I would like to end the talk. So with this, I end my discussion and I can have a couple of questions.
Yeah, thank you.
And one more thing, and if anyone is interested in going for the code and for any collaboration, these are my details for my email ID and my LinkedIn and my website. So you can kindly contact me and we can seek for further research opportunities also. Okay, thank you.
Thank you, Dr. Sengupta. It was quite a informative and nice session. So here we have Bankachan Gorai who has some questions to ask. So Bankachan Gorai, can you just go ahead with your questions, please? Maybe I can ask a question on his behalf. So if two teams play a football game, can model predict which team will win?
It depends upon the input features. Now, for a single PC, this question is the outcome of the discussion or the example that we did. If we say if there is a football match, means two teams are playing, and we are trying to predict whether team A is winning or not. If team A is winning, then out of the two teams, the team A is winning, and if team A is losing, then definitely team B is winning. So it's like it's like a vice versa effect. Now we can say that if it is a draw or not. Again, in that scenario, the process will be same, going through the features and calculating, and then seeing what is the importance of that, and then selecting the topmost features in the inputs. It will predict, but again, explainability, interpretability, and definitely chances are there.
Okay. Another question from Sanjay Roy is what can be the application for Xi in gene data analysis?
Okay, in gene data analysis, if right now I am working a bit about gene sequencing, and in that explainability, if you see, if there is a sequence of chains, if you are working on gene sequencing, suppose there is the sequence of characters given in the gene sequence. Now, if we go by the history, and if we are suppose using the gene sequence, we try to predict, say, for example, autism. Okay, if there is this person, if this person is going to suffer from autism or not. In that case, if we are going through the gene sequencing and we analyze the sequences, we build a model, and at every sequence itself, we can go for local this explanation. Means what I am working on, it is a local explanation in that case.
Okay. Another question from Somik Shah is, sir, can you please explain me what is the artificial general intelligence, AGI?
Can you pardon the question once more?
Yeah, he wants to get an explanation on the AGI, artificial general intelligence.
General AI, general artificial intelligence.
Yeah,
Okay.
yeah.
Okay. See, now this is not with explainable AI. This is more with AI. Okay. Now what happens in AI? Let me give you an example. Let us go with the dogs and the husky and the wolf. Now in the ImagiNet, if you go to the ImagiNet library, it's free in the Google. You can go there also. There are classifications and there are labels. Okay. Now normally, if you are working on labels, means I am having 10 pictures. In the bottom of the picture, it is written that these are dog pictures, these are wolf pictures. Okay. So I earlier itself I know the before designing the model itself I know the label, so it becomes easier. Now that is supervised learning. Another learning you might be knowing is unsupervised learning. In unsupervised learning, no labels are given. That means I am given a picture, I don't know whether it is a dog or a cat or a cow. Now depending upon types of features, I am going to cluster them among different places. That is unsupervised learning. Another is the general reinforcement learning that is coming into the picture. Now in reinforcement learning also, there is no labels. It is, you can say it is a semi super unsupervised part of thing. In reinforcement, there are policies that are being taken. You make a policy, you go ahead along the policy, and then when you fail, again compile, you give points to the policy, and then again you start a policy from any point depending upon the number of points that you have given. General artificial intelligence is, as you have asked me, deals less with supervised, more with unsupervised, and the most with reinforcement learning. General artificial intelligence is, you can say that when machines start thinking like humans. We are a general artificial, we are generally intelligent. I mean, humans are general intelligent, are having general intelligence. When machines come up with the human-like intelligence, then we can say that those are general artificial intelligent models. But now, till now, Xi is in a nascent stage. Artificial intelligence has gone a long way, but again, it has very high scopes and domains and opportunities for growth also. AI is also growing. AI is also growing. Xi is also growing. Is it?
Yeah, another question from Saival Sarkar. Could you please let us know the level of acceptability of medical Xi being developed in Indian hospitals?
Okay. Actually, I asked this question to one doctor itself. Okay, I asked about the AI. I will quote that itself. I asked him that what is the acceptability of the accuracy? Means accuracy acceptability. At that time, I was building a model on diabetic retinopathy. So I asked him about the acceptability of the accuracy. Means how much accuracy is acceptable for predicting whether this person is going to have diabetic retinopathy or not. Now, at that time, I asked him that, see, in case of eye, you are saying that this is the X amount of accuracy, that is minimum requirement for saying that the model is good enough, pretty good enough. But again, if I go for the dermatology, the skin cancer cases or the oral cancer cases, will the accuracy vary? Or in case of the stroke prediction, will the accuracy vary? Now, if the accuracy depends upon the type of medical issue, then Xi will also depend upon the type of medical issue. Am I clear? If my model prediction accuracy, whether 80% accuracy is good for skin cancer, or it requires 85% accuracy, or it requires 90% accuracy, when these will be stated, what is the accuracy of the model that is acceptable for this certain type of disease or this certain type of healthcare, that will be the, you can say, the causal effect for the explainable AI also. That will depend upon the accuracy, acceptable accuracy of the normal AI model, and then you can go for the accuracy of the Xi model.
I think that's all from the questions and answers arena. So thank you, and may I ask Dr. Raju Boshak to have the vote of thanks.
Yeah, thank you very much. Is it audible?
Yeah,
hello.
Audible. Yeah,
yes,
audible.
Yes.
Oh, thank you very much for giving me the opportunity to propose the vote of thanks. Thank you. It is my
Let me,
proud privilege to extend my sincere thanks and gratitude to all the distinguished participants in this webinar on the theme Explainable AI, the need for trust, organizing by the Computer Engineering Division, West Bengal State Center, IEI through online platform Zoom. So my sincere thanks also goes to the panelists, Dr. Diganta Sengupta, Associate Professor in Department of CSE and faculty in charge of Department of Computer Science and Business Systems, Meghnad Institute of Technology, Kolkata. My sincere thanks also goes to Dr. Nirmal Das, Chairman, West Bengal State Center, IEI, Dr. H.O. Thakre, President, IEI, Mr. Sandeep Kumar Dev, Vice President, IEI, Mr. Amit Kumar Das, Chairman, Computer Engineering Division Board, IEI, Dr. G. Ranganath, Chairman, CATE, IEI, Dr. Soival Sarkar, Deputy Director General and State Informatics Officer, National Informatics Center, West Bengal, and Chairman, Computer Engineering Divisional Subcommittee, West Bengal State Center, IEI, Mr. Sujay Chaudhary, Senior Technical Architect, Mindtree, and moderator of this program. And my vote of thanks also goes to all members of the Council and Division Board members of CPDV, all members of the Committee of West Bengal State Center, IEI, and all members of the Computer Engineering Divisional Subcommittee, Director Technical, IEI, and his team for wholehearted support. My last but not the least, my sincere thanks also goes to those persons who are behind the screen and giving their silent support to make the program grand success. Thank you all. Thank you very much. Um, a very good night to all of you. Thank you very much. We
okay,
are concluding the today's program here.
before concluding, let me have some few words, please. I am Amit Das, Chairman, CPDB.
Yes, sir. Go ahead, sir. Yeah. Thank
Okay.
you. Thanks
Thank you
for
so
joining.
much, Professor Sengupta. Yeah, thank you so much, Professor Sengupta, for bringing out this topic so well. While AI is being explored widely, the explainability is very much required, especially in cases related to ethical use cases in health sector, as well as where it gives diverging results for acceptance. Professor Sengupta, you gave very apt examples, the asthmatic case, the pneumonia wala, and the husky and the wolf example, the football, as well as explaining out the explainability and the interpretability example to bring out the case in a very good storytelling mode. So I also congratulate IEI West Bengal Local Center, West Bengal Center for this wonderful technical seminar. Thank you so much. Thank you so much to all of you.
Thank you, sir, for your nice speech. And with this, we will be concluding this today's webinar on this trust enabled AI and all this. Good night to everyone who has joined, and thank you for everyone for having this great session on this. Thank you.
Thank you.
Yeah, thank you.
Thank you, sir. So with the permission of chair, I'm ending the webinar here.